In this video, we're going to focus on memory systems that will have memory in. But before we get too far, we need to talk about how do we build a single bit of memory. And a single bit of memory may be referred to as flip-flop. We might also refer, you might also hear referred to as a latch, or of course a single bit of memory. Okay, so those are the common name. I'm sure there's much more names that you can come across it, but those are the real common ones we use. And SR Flip Flop, it stands for set / reset flip flop. And it's not in heavy use right now because we have a simpler version of it, but it's a great one to get introduced to how flip-flops work, how memory bits work. And then we'll move on to the more simpler to use devices later. Okay, so these device memories will be used in systems that we would refer to. Up to now, all the logic we've been doing has been a combinational logic. So if somebody tells you about a combinational logic, they basically are saying that has no memory. Whatever the input is, so if a combinational logic, basically the distinction is no memory. You give it an input, you get an output, and your output has no implication on the future. Then this kind of logic we're going to be talking about in this chapter is called sequential logic. So they have a sequence to them. You might also sometimes hear it referred to, actually more commonly referred to as the finite state machine. Okay, and they abbreviate that to FSM, finite state machine. So these are the same thing, different name for the same thing. And the distinction here is that they do have memory. Okay. Now that we've kind of done a little bit of a definition, let's go ahead and go back and take a look at seeing how we build the memory. Here is a great example of an SR flip-flop. This is not the only way to build an SR flip-flop, but this is one way to build an SR flip-flop. And if you look at this picture and think about it, what is the difference this picture has compared to everything else we've been talking about so far, all the combinational logic we've talked about so far? And hopefully you will see there's a couple of interesting things. One piece of interesting thing is this delay. Another piece of interesting thing is these lines that go back. See that? In the past, we've never had outputs that flow back and forth. These are called feedback signals. And this particular feedback signal is a delayed signal. And if you notice here, we have a Q plus and we have a Q. This is a new concept because if you notice, Q is exactly Q plus, but some small amount of delays later. How hard is it to build delay? Very easy. This here is a one simple way of making quick delay. Right? Remember, each inverter has a delay in it. So this could simply be the delay block we are talking about. There are more sophisticated delay block, but that's good enough. This Q plus is referred to as the next state. That's basically the value that's stored in the memory. This is available to the outside world and is called present state. So now we introduce a new concept. Is that we have a present state, we have a next state, and the only difference is that present state is going to become equal to the next state, or if you want to think about next state will become present state in a short amount of time, however amount of time, for example, it takes to go through 2 NOT gates. Okay, but then the important part is that this next state will come back and impact, notice that, impact the next state. So that's something we need to really pay attention to. Now, if we write the equation for Q plus right here, that is equal to S or Q naught, S or Q not over the whole thing, or with R not over the whole thing. And this equation describes Q plus and is referred to as an characteristic equation, an important one to remember. Okay, so now that we have a characteristic equation, can we write a truth table for this? Yes, we could. So let's go ahead and take a look at a truth table for this thing. Now remember, the only thing we have to be cautious about is that if we do a truth table for this, we're going to have two inputs, right? Two external inputs. These are called excitation input, excitation input, or you can think about it as an external input if you like as well. And then for this case, and then Q is the present state and Q is the next state. As you notice that the present state Q is actually going to become an input itself into our system. So the truth table for here, it wouldn't make sense, because if I had a truth table, I would have S and R, which are our external input, and that should be all I need. But since this thing has a feedback, I have to also worry about Q, because now Q is also my input. By the way, they don't call this truth table anymore. They call this present state next state, because it has the present state and it will have the next state here. Okay. All right. So that's good to know. Present state, next state, very common. This is too long to say, so we will call it basically PS-NS table. So truth table is gone. PS-NS table, present state, next table, is taken over for it. Now, Q plus is driven by this equation, so Q plus is what is going to tell us what's going to happen here. Writing this is just like what we used to do for truth table. You have to write all the possible situations that can happen. Oops. And then we'll have to take all of these pieces of information and go back and fill out the Q plus. You can take a minute and try to do that. And all we are doing, we're taking Q is 0, S is 0, which means this will be a 1, but R is, so the R is 0, so this whole thing is a 1, but it's inverted, so it's a 0. So 0, 0, 0 will be called 0, okay? 0, 0, 1, if you put that in there, that is also 0. And then we'll go to the next one, and it looked like I missed one once again. There's one I missed right here, 0, 1, 0. And when that happens, we get a 1. And then 0, 1, 1 will 0, okay? And then I'm just basically what I'm doing, I'm taking these values and plugging them in the characteristic equation. And then 1, 0, 0 will give me 1. And then 1, 0, 1 gives me a 0. And 1, 1, 0 gives me a 1. And 1, 1, 1 gives me a 0. Okay? Assuming I fill this correctly, now this is something interesting happened. In the truth table, once you got the output, it was done. The problem here is that when the Q plus changes, that means in a short order your Q will change as well. So these are these states that happen where a Q and Q plus are different, are called the, they're not a stable state. They're kind of unstable. So let's just put a few words in here just to make sure we can keep track of it. So whenever we have Q and Q plus the same, let's make a designation on it, okay? So the comments for this one would be is Q is 0, and that's called a hold state, okay? That will result in a stable system for us. Then Q goes from 0 to 0, that's a hold. And by the way, we're also going to be able to say it's a hold 0 because it's holding 0. And then if you look at this one, you went from 0 to 1, is not a hold, is changing and is setting Q plus. So in a short order, Q will be 1. Now the question is, will that make any changes to us or not? We'll have to wait and see. And then here we are going from 0 to 0. So once again, we have a hold and is a hold 0. Normally, this doesn't make sense under the terms we are using here because it is set and clear. You can't have set and reset both be 1. But anyway, it's there and it's 0. And because of this equation gives us 0, we're going to write a 0. And then we got 1 staying 1, Q and Q0, so that's called a hold 1. And then the rest one is reset, fine. Then it makes sense, set is 0, reset is 1. So it's going to be that. And then this one is hold 1. Okay, and this last one is actually going to be, once again, because the set and reset are once, we usually say is normally not allowed, but it's there and we're going to get a 0. But that is also going to be, it's just going to be resetted, right? It's been changed to 0. Okay, so now what we're going to be able to talk about here is the cases where they're hold, they are stable. That means basically when Q plus moves to Q, you're just going to stay here. Everything is all good and dandy. For this one though, it is still Q is 0, so you're going to stay here because nothing changes. Q and Q0 are the same. But notice what happens here when we go from 0, 1, 0 and we get a 1, all of a sudden this will no longer go back here. When Q plus becomes a Q, then you are moving from here all the way down to 1, 1, 0. You see that? Okay, so you'll go there and that's a hold. So this one is an unstable because after a little while you move down the row to a different place. Do you understand? So this Q became a 1, which means now your state is going to look like this, 1, 1, 0 instead of 0, 1, 0. And then this one is a hold, this one is a hold, so nothing interesting is happening. This is another place that something interesting might happen because if you look, let me use a different color, it's getting kind of messy. So if I come to this reset state, my Q plus is now here, which means over a short period, Q is going to change. If Q changes, I'm going to end up at 0, 0, 1, 1. So this state actually goes up here. And then at that state is stable. So this is another unstable state. And finally, the last one is this one, which is unstable because this 1, Q1, is going to shortly change because Q plus is 0. So eventually I'm going to move all the way up here and then I'm going to be, so we have a few unstable states, okay? Now, before we go too far, this is kind of complicated to work with. So remember we had these table compression business we talked about a little while ago. If you move the Q to the least significant bit and compress it around Q, something interesting happens. So if you do that, then you're going to have S and R on this side, and you have the next state in here. And what you're going to see is 0, 0 is Q. That's where the memory comes in here. If I'm 0, 0, whatever my current state is going to stay. It's not going to change. And then 0, 1 will force me to a reset state. 1, 0 force me to a 1. And 1, 1 forces me to 0. By the way, if somebody asks you, this is called a reset dominant. And the reason for that is if I set and reset on, it's going to reset. This table, this is the why we did all the videos about compressing truth table. This is what we call the SR Flip Flop characteristic table. Okay? And you remember what the characteristic equation was. The characteristic equation was this thing. So the characteristic equation is Q plus is equal to S or Q, not or R, not over the whole thing. Okay, so these are important for every flip-flop we're going to talk about. You need to be literally know both the characteristic table and the characteristic equation. Okay, now let's go ahead and do one more thing before we leave this alone. Another way, and that's not done commonly, but another way to describe flip-flop, we can take this present state next table and do a K-map for it. Okay, so if you do a K-map for this, we will have S and R here and Q here, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And I'm just basically going to take the values here and plug it in here. I'm going to have, and I have, it's a little twisted the way we wrote it, so it would have been easier if I took the Q and made it the least significant bit, but I think we can survive. We'll see, this is 0, this is 1, this is 0, 0, 0, 0, 1, 1. So that's basically that table, but now we go and think about this thing. So this is basically the K map showing the Q plus. Let me get a different color of, maybe this time blue or whatever. Oh no, not blue. Let's go ahead and get it red. Now if you notice here, S is 0, R is 0, Q is 0, Q plus becomes a 0, which means it does not change. This is, they draw a line under it indicating it's stable. If S is 0, R is 0, and Q is 1, because the table tells us if it's S and R are 0, Q will not change, that is a stable one too, because Q was 1, Q plus is 1, nothing is going to change. Okay? When Q is 0, R is 1, 0, 1, then and Q, that we don't care, is going to always be 0. So this is going to be 0. We came from 0 to 0. All is good. So that's stable also. Okay. Now, for 0, 1, take a look at 0, 1, 1. 0, 1, 1 basically makes sure that if you get 0, 1, then you're forced to resetting. So when you reset, Q shortly will be, this will actually move from here to here. And I shorted it. So we're not going to put an underscore here. This is an unstable state, and it was the same over there in the present state next table. So this kernel map is built on the present state next state. Now, if you look at down here, you'll see if you got 1 and 1 and Q is 0, the next Q plus is going to be 0, so it's a stable state. So, and then this is a stable state, the rest are unstable because they move someplace else. For example, for S is 1, R is 1, Q is 1, it becomes a 0, which means the next one is going to be moving over here. Okay, so that's unstable. And here we got a 1, 0, 0, but since it's a set, it's going to move here. So only have, out of the 8 locations, we have 5 stable and 3 unstable. So that was another one. Okay, so these were many different. So this definitely is the one called characteristic equation, characteristic table for SR flip flop. Those what drives everything. But we have many different ways of showing this thing. So these are a couple of ways to show it. Another one. So we've already talked about present state, next state diagram. Another way to show the functionality of this is called state diagram. So state diagram is another good way of doing this, and that basically says what I'm going to do is for every possible value of Q, and I'm going to have a bubble. So they draw a bubble for every possible value of Q. So let's do a box around it. So, but before we do anything else, we need to tell the world how we're going to write it. So I'm going to write whatever the value of Q is in the bubble, and on the branch, I'm going to write whatever the value of S and R are. Okay, this is called a legend. Every state diagram should have a legend to tell people what they mean. So let's say I have Q, there's only two possible values Q can take, 0 and 1. And then now the question is, if I'm in state 0, 0, where do I go to learn this? So I'm in state 0, 0. I'm in state 0. Q is equal to 0. What possible value? Well, I can get any of these other possible values of that. So if I'm in 0 and I get 0, 0, I'm going to stay here. So I'll write 0, 0. Okay. If I'm in 0 and I get a 0, 1, I'm going to stay here also. Okay. So you can write them with a comma separating them, I suppose. And then if I'm in and I get a 1, 0, then I'm going to move over here. See how the arrow shows you where you go depending on what you get, and he tells you what is on the what's on the branch. So 1, 0 does that, and finally 1, 1 keeps you right here. So that's a 0. Then I go over to 1 and I say, okay, well, now if I'm on 1, Q is equal to 1, and I get 0, 0, what happens? You say, okay, I'm going to stay right here. What happens if I'm in 1 and I get a 0, 1? If I get a 0, 1, I'll go to 0. And if I get a 1, 1, I go to 0, and I'll stay here if I get a 1, 0. So this is called the state diagram. As you can see, this characteristic table describes how the flip-flop works. The present state, next state describes it. And this is another one. Truth table does not describe it. So we'll come back to something we called, actually this should be 3. We'll make that a 3. We'll go ahead and clean this up a little bit. So let's make that 3. Actually, there's another one called the timing diagram, which also could describe how it works, and we'll come back and talk about that. All right. ASM chart is a variation on this one, and it's attractive because it's more of an if then else situation. It's just basically we do a square for every possible case of Q equal to 0, and then these are states, and then we have Q. Oops, shouldn't draw the line in the middle. And Q is equal to 1, okay? And then we do an if then else concept. We say we are in 1, and then we'll look to see what we got. If I'm in 1, either got a 0, 0 or 1, 1. If the answer is yes, I'll go back here. Okay? If the answer is no, I go up here. Okay? And then if I'm in state 0, I'll do a check, similar check. Okay? And I said, is it 1, 0? Well, that's S and R. I'm sorry, these are SR equal to that. SR equal to that. Is it equal to 1, 0? If it's a yes, if it's a yes, I'll go to 1. If it's a no, I'll go back here. Okay, this is called the ASM chart. It's really kind of nice if you need to write a program to implement these maps. We are most commonly use this. If we are left by ourselves, we always use state diagrams. A lot easier to think about it and work through it. Time diagram, we don't do it, and when we do it for very, very special cases. And the reason we do it is we want to know the timing diagram. None of these other ones give you the timing diagram. So what we're going to do, the timing difference between things. For example, we in here, in none of the other diagram we can do that, but in here we could say S, R, and then Q. And let's say we have a set high goes to low, and then we have a reset which is low and at some point goes high. I can literally show that the Q is the set comes, we don't know what Q is. Let's say we don't know what Q is up to here, so we'll usually show it this with a question mark on it. But at this point, right when this set goes, oops, sorry, I drew this incorrectly, so let me go ahead and erase and do it. So let's say set was low and at this point went high. So what I'm going to do is, we don't know what the value is, but at this point we know it's going to go high, but we can actually show that it's sometime later and be able to show the tilted difference that it took for this to go up, okay? And then when this goes up, we know 1, 1 causes Q to go down. So anyway, the timing diagram is basically a diagram, the x-axis is time, and allows us to show all these delays. None of the other one allows us to show the delays, and if that delay is an important thing, then a timing diagram is what you want. Let's do a quick summary of all the things we've gone. We've gone through a lot of different things here. We started the conversation by talking about what is a flip-flop and introduced the SR Flip Flop. Along the way, we showed that this is the first time we have a case where an output is actually fed back as an input, and the Q, which is called a state, is the condition where the flip-flop is currently. Q plus, they put a plus on the Q, and that makes the next state. That means in a little bit of time, Q becomes Q plus. Then we describe both the present state, next state, which is like a truth table, except it's got present state and next state in it. And if you eventually have some output that you create, they go all the way here, and we'll have plenty of time to talk about that. And then each flip-flop, this is our first one, the set reset is the first one. It'll have a compressed table called the characteristic table, and then of course that's based on the characteristic equation that is based on the circuitry we built. Okay, and then we showed the K-map, we talked about the stable states, and then we talked about how the 4 different ways we can describe the functionality of a flip-flop. One is present state, next state, state diagram, ASM chart, and timing diagram. That brings us to the end of this segment.